In a remote corner of the cosmos, nearly 13 billion light-years from Earth, astronomers have uncovered something that defies every expectation. Colossal galaxies, so massive and so mature, appear to be older than the universe that contains them. These luminous giants, shining like ancient cities suspended in darkness, hold as many stars as the Milky Way, yet somehow emerged when the universe was still in its infancy, barely 500 million years old. We're about to explore discoveries so extraordinary, they're forcing scientists to rethink the most fundamental assumptions in cosmology. We will examine galaxies that seem to break the laws of physics and dive into theories suggesting the universe may be far older than we ever imagined. Before we begin, make sure to like and subscribe, because what you're about to hear challenges the very framework of reality. When the James Webb Space Telescope began sending back its first images on July 11, 2022, astronomers expected soft, blurry snapshots of the universe's childhood. Instead, they saw giants. One tiny red speck on Dr. Erica Nelson's screen was supposed to be a dim, primitive galaxy, still struggling to form its earliest stars. But the data poured in, and her software returned numbers that made her freeze. Distance: 13.1 billion light-years. Mass: 100 billion stars. This object held as many stars as the Milky Way, yet existed when the cosmos was only 700 million years old. Finding such a galaxy is like discovering a fully grown oak tree in a nursery of saplings. According to every model of galaxy formation, this should be impossible. The Big Bang model tells us that after the universe erupted into existence 13.8 billion years ago, hundreds of millions of years had to pass before the first stars were born. Those stars then needed to live, explode, and seed the cosmos with heavy elements before complex galaxies could form. Building something on the scale of the Milky Way should take billions of years of cosmic recycling. Yet this galaxy seemed to bypass the entire process. Its ancient light, its heavy elements, its surprisingly mature structure, all of it contradicted our most trusted timelines. If the universe was so young, how did this galaxy assemble so quickly? The discovery sent shockwaves through astronomy. Something fundamental wasn't adding up. Either our model of galaxy formation was deeply flawed, or the universe itself is older than we think. Some scientists even whispered the unthinkable. Perhaps parts of the Big Bang Theory need to be rewritten. And this was just the beginning. Within months, more and more of these impossible galaxies appeared across Webb's images, multiplying faster than anyone expected.
Each new observation only deepened the enigma, chipping away at the pillars of modern cosmology. And that first tiny red dot, it was merely the opening piece of a cosmic riddle that would push humanity to rethink everything we believed about the universe's beginnings. For over a century, we've assumed the universe follows a rigid cosmic timeline. According to the standard Big Bang narrative, the first 400,000 years were pure chaos, an opaque, blisteringly hot plasma where even basic atoms couldn't exist. Only after this primordial fog cooled did hydrogen and helium finally stabilize. These simple atoms drifted through the darkness for another 100 million years before gravity could gather them into dense clouds, igniting the first stars. Those first stars, titanic, short-lived giants, had to live fast and die violently. Their supernova explosions forged heavier elements like carbon, oxygen, and iron, scattering them across the young cosmos. Only with these ingredients could the next generations of stars and galaxies begin to take shape. By all scientific reasoning, building a large, complex galaxy should require at least 1 billion years of cosmic construction. It's the skyscraper analogy on a universal scale. You need foundations, then beams, then floors, and finally the fine structure. The universe was supposed to follow this slow, orderly blueprint. But the galaxies revealed by Webb seem to break that timeline completely. They contain heavy elements that shouldn't exist yet, mature stars that shouldn't have formed, and structures far too organized for such an early epoch. It's as if a towering cathedral appeared out of thin air, built in a single afternoon. The math simply refuses to cooperate. If the universe is 13.8 billion years old and we're observing galaxies from 13.1 billion years ago, that leaves only about 700 million years for these systems to assemble. Yet everything we know says they would need 2 billion years, at minimum, to reach the sizes Webb is detecting. This timeline crisis has forced scientists to entertain three radical possibilities. Galaxy formation happens far faster than any of our models predict, perhaps 100 times faster. The universe could be significantly older than 13.8 billion years, or the Big Bang model itself contains fundamental flaws. Something in the cosmic clockwork is out of sync, and the schedule we thought governed the universe no longer fits the evidence. Among Webb's thousands of discoveries, one class of objects burned especially bright, tiny crimson pinpoints known as little red dots. These objects were completely invisible to older telescopes, yet Webb revealed them as some of the most important clues in this unfolding mystery. Unlike typical galaxies that emit light across a wide spectrum, these strange objects glowed almost exclusively in infrared, vanishing at shorter wavelengths. Their extreme redness meant they harbored something astonishing, either ancient populations of stars or voracious supermassive black holes feeding in the young universe. When astronomers examined the first of these red dots, they were stunned. It contained nearly 100 billion stars, massive enough to rival the Milky Way, yet existed when the universe was only about 5% of its current age. It was the cosmic equivalent of walking into a nursery and finding a fully grown adult among newborns. And the redness itself told an unsettling story. Early galaxies should be bright and blue, filled with young, blazing stars. Red galaxies are supposed to be ancient, their stars having burned steadily for billions of years. But how could something that old exist so close to the universe's beginning?
But these mysterious red dots seemed to break every rule at once. They appeared in the universe's infancy, yet carried the spectral fingerprints of systems that should have taken billions of years to mature. They were paradoxes, objects that looked both newborn and ancient, like finding fresh footprints fossilized in stone. As Webb uncovered more of them, the pattern became impossible to ignore. These weren't rare oddities, they represented an entire class of massive early galaxies that simply shouldn't exist. Some estimates suggested there were 100 times more of these objects than standard cosmology allowed. The universe looked far too busy, far too evolved, far too soon. The scientific community fractured into competing interpretations. One camp argued that the red dots proved galaxy formation in the early universe must have been shockingly efficient, so efficient that our models were off by orders of magnitude. Another group insisted these objects were illusions, their redness caused by supermassive black holes blazing brighter than the galaxies around them. But a growing faction of cosmologists dared to consider a far more unsettling possibility. What if the red dots are telling us the universe itself is not what we think it is? Inside any normal galaxy, the birth of stars is a slow, regulated process. Clouds of gas collapse over millions of years, forming new stars at a pace constrained by physics, temperature, and turbulence. But the early giants revealed by Webb seem to fast-forward this process beyond anything science currently allows. To assemble a galaxy containing 100 billion stars in just 700 million years, star formation would need to operate at nearly perfect efficiency, something our models say is flat out impossible. Under ideal conditions, galaxies can convert only about 10% of their available gas into stars. The rest is blasted out by stellar winds, supernovae, and radiation pressure. It's like a factory where only a small fraction of raw material becomes finished product. But these primordial giants appear to have operated at almost 100% efficiency, leaving no gas unused. Every atom of hydrogen and helium seems to have been turned into stars. No waste, no leftovers, no time for hesitation. The energy problem makes this even stranger. Massive newborn stars release fierce stellar winds that heat the surrounding gas to millions of degrees. That hot gas usually escapes the galaxy, stopping further star formation, like a built-in cosmic safety valve. So how did these early galaxies override this natural shutoff switch? Some theorists suggest the early universe's higher density may have kept gas gravitationally trapped. Others propose that dark matter halos in the ancient cosmos were far deeper and more compact, creating stronger wells to hold star-forming material in place. But every computer simulation trying to recreate these conditions runs into the same wall. Either they fail to produce enough stars, or they create unstable galaxies that should blow themselves apart from their own intense energy output. But there they are, galaxies that folded billions of years of evolution into a tiny sliver of cosmic time. Galaxies that behaved as if the universe hit fast forward, galaxies that should not exist, but undeniably do.
The implications extended far beyond ordinary astronomy, hinting that the very blueprint of how the universe operates might need to be rewritten from the ground up. At the core of every massive galaxy lies a supermassive black hole, cosmic titans containing millions or even billions of solar masses. But in the early universe, these gravitational giants are an even greater enigma than the galaxies that surround them. The red dots uncovered by Webb don't just contain impossible numbers of stars, they also host black holes that should not exist under any known physical timeline. The light from these objects reveals the unmistakable signatures of violently feeding black holes, gas spiraling inward at extreme velocities and heating to millions of degrees. This process unleashes quasar-level brilliance among the brightest beacons in the universe. But there's a problem. Growing a supermassive black hole takes time, a lot of time. Like fattening a cosmic predator, material must fall inward steadily, and physics imposes a natural speed limit. Known as the Eddington limit, this boundary determines the maximum rate at which matter can be consumed before radiation pressure pushes new material away. Even if a young black hole were fed continuously at this absolute maximum, it would still take hundreds of millions of years to grow from a stellar mass seed into a supermassive colossus. Yet, the black holes detected in these primordial galaxies seem to have achieved that growth in a tiny fraction of the available time, so fast that they would need to consume matter at 5 times the Eddington limit for their entire lifetime. It's like claiming someone gained 1,000 pounds by eating one small meal a day. The math refuses to cooperate. Even more troubling is the question of their origin. The traditional view says supermassive black holes formed from the deaths of the universe's first massive stars. But those first stars need time to be born, burn, explode, and collapse, leaving almost no time left for rapid black hole growth. This paradox has forced scientists to consider radical alternatives. Some now speculate these black holes formed directly from the collapse of enormous primordial gas clouds, bypassing the entire stellar life cycle. Others entertain the possibility of primordial black holes, objects created in the earliest fractions of a second after the Big Bang, acting as ready-made seeds for later growth. But even these explanations may not solve the mystery, because the universe might be playing an even more deceptive trick. What if some of these supposedly massive early galaxies aren't massive at all, but cosmic illusions created by their central black holes? Recent studies suggest that many of Webb's early galactic giants could be optical mirages. When gas spirals into a supermassive black hole, it forms a blindingly bright accretion disk, heated by friction to extraordinary temperatures. This disk can shine more brilliantly than the combined light of billions of stars, overwhelming the view of the galaxy behind it. It's like trying to count candles in a dark room while someone points a stadium floodlight directly at your eyes. The glare erases the details. Similarly, an actively feeding black hole can cloak the true size and structure of its host galaxy, making a normal-sized system look like a cosmic heavyweight.
The revelation offered a tempting way out of the impossible galaxy dilemma. If many of Webb's mysterious red dots were merely ordinary-sized galaxies, whose brilliant cores were powered by aggressively feeding black holes, then perhaps the universe wasn't breaking its own rules. Perhaps the early cosmos didn't need to build behemoths overnight. But the mirage solution quickly ran into its own contradictions. Even if these galaxies were smaller than they appeared, their central black holes were still far too massive for such an early cosmic epoch. The illusion hypothesis simply shifted the impossibility from the stars to the black holes, and detailed observations made it clear that some of these red dots contained genuinely huge stellar populations alongside the quasar-like signatures. These weren't just bright objects. They were objectively gigantic, billions of stars assembled in what amounts to a cosmic heartbeat. The mirage effect might explain a fraction of the anomalies, but it could not erase the full population of early giants in Webb's data. Many were both massive and luminous, demanding that the universe found a way to fast forward its own evolution in ways completely foreign to current physics. As astronomers strained to separate the true titans from optical deception, a far older and far stranger idea crept back into the conversation. An idea pulled from the shadows, a scientific history. In 1929, at the same time Edwin Hubble argued that galaxies were racing away from us, Swiss astronomer Fritz Zwicky proposed a radically different interpretation. What if galaxies weren't moving at all? What if light itself was changing as it crossed the universe? Zwicky suggested that photons might gradually lose energy over vast distances, a process later called tired light. As light aged, its wavelength would stretch toward the red, mimicking the redshift normally attributed to cosmic expansion. Under this view, the universe wasn't expanding. It wasn't even young. It was static, ancient, and eternal. For decades, tired light was largely dismissed. It failed to explain why distant galaxies appeared smaller than expected, and it couldn't account for the cosmic microwave background radiation, the Big Bang's afterglow. But Webb's discoveries have revived interest in the once-abandoned idea. If the universe isn't expanding, then distant galaxies aren't being viewed in their infancy. They are being viewed at their true age, which could be far older than Big Bang cosmology allows. Massive early galaxies would no longer violate physics. They would simply be ancient. Recent theoretical work has attempted to merge tired light with the possibility that fundamental physical constants, such as the speed of light or gravitational strength, may have changed over time. In this combined model, the universe could be 26.7 billion years old, nearly double the official age. In such an ancient cosmos, galaxies would have had plenty of time to grow vast and mature long before their light reached Earth. This revival of tired light is not just an alternative explanation. It challenges the deepest assumptions of modern cosmology, especially the belief that the universe's fundamental constants are unchanging. What if they aren't? Some quantum gravity theories have long hinted that constants may evolve as the universe ages. If early physical laws differed even slightly from present-day values, then star formation, black hole growth, and galaxy assembly could have unfolded far faster than our current models allow. A universe with variable constants is like a cosmic machine with adjustable settings, a universe whose physics may not have always matched the rules we observe today. Some cosmologists now explore hybrid models, in which changing constants paired with tired light elegantly reconstruct a universe nearly 27 billion years old. In such a scenario, the early cosmos operated under different physical laws that accelerated structure formation, while tired light explains today's redshift without requiring cosmic expansion. The math is beautiful. The implications are explosive, and the controversy is only beginning.
Critics argue that altering the universe's fundamental constants would unleash consequences across all of physics, consequences we simply do not observe. Such changes would ripple through everything from the cosmic microwave background to the very formation of the first atomic nuclei. For the idea to work, these constants would need to shift in exactly the right ways at exactly the right times, a level of cosmic fine-tuning that makes many scientists uneasy. Supporters counter it with a simple question: how can we be certain the laws of physics have always been the same? They argue that our current models already rely on invisible ingredients, dark matter and dark energy, to remain functional. If we are willing to accept 95% of the universe as unknown, then perhaps variable constants deserve a place at the table too. The debate ultimately touches something deeper than astrophysics. It forces us to confront what scientific truth really means. Are the laws of nature fixed for all eternity, or do they evolve alongside the universe they govern? While theorists wrestle with these philosophical earthquakes, Webb's galaxies remain in the sky, defiant, ancient, and uncomfortably real. Simulating the impossible. When observations begin to break the known laws of physics, astronomers turn to their most powerful instrument, supercomputer simulations. By constructing digital universes governed by established physics, scientists can test whether nature could produce the galaxies Webb has revealed. The earliest simulations offered a clear verdict. Under standard physics, these galaxies cannot exist. No matter how researchers arranged the ingredients, the models repeatedly produced small, primitive galaxies, nothing like the colossal, mature systems observed at cosmic dawn. But as simulations became more sophisticated, a surprising possibility emerged. What if the early universe went through short, explosive eras of star formation? Brief cosmic frenzies during which galaxies built stars at rates unimaginable today. These hyper-starburst events would ignite when young galaxies collided, funneling enormous clouds of gas into their centers. The resulting gravitational pressure could ignite a chain reaction of star formation powerful enough to compress millions of years of evolution into a geologic instant. For a short time, a galaxy could convert nearly all of its gas into stars, something modern galaxies cannot do. Simulations showed that such events might make a young galaxy appear as massive as a modern giant, even if its true stellar mass was far smaller. Dust also played a key role. Freshly formed stars produce dust that absorbs blue light and re-emits it in infrared wavelengths. In Webb's eyes, this makes galaxies appear redder and heavier than they truly are. Together, extreme starbursts and thick dust clouds might provide a bridge between theory and observation. The early universe may not be breaking any laws. It may simply be far more violent, chaotic, and efficient than we ever imagined. The oldest signal in the universe takes the stand. Floating in the static between radio stations lies the most ancient light ever detected, the cosmic microwave background, the afterglow of the universe's first moments. This radiation, released when the cosmos was just 380,000 years old, is one of the strongest pieces of evidence for an expanding universe. Its temperature map is astonishingly precise, matching Big Bang predictions down to tiny fluctuations that seeded every galaxy and cluster in existence. But tired light theories face a daunting question. How do you explain the cosmic microwave background if the universe isn't expanding? In the standard model, this ancient light cools naturally as space itself stretches. In a static universe, however, the same radiation would require an entirely different and unknown mechanism to exist at all. Supporters have proposed several alternatives. The CMB could be accumulated starlight, redshifted over billions of years, or it might arise from photon interactions with a cosmic medium, or from still unknown physical processes that mimic a perfect black body spectrum. Recent attempts to model these ideas show they are not impossible, just far more complex than the elegant predictions of the Big Bang. The CMB also reveals something else. The early universe was unbelievably smooth. Regions too far apart to ever communicate somehow shared the same temperature, the same structure, the same physical conditions. This horizon problem hints at deeper mysteries about the nature of space, time, and the universe's true history, mysteries that neither expanding nor static models have fully solved. As telescopes continue mapping the CMB with increasing precision, this ancient whisper from the beginning of time remains a central witness in the ongoing trial between competing cosmological theories.
In the standard cosmological framework, dark matter makes up roughly 85% of all matter in existence. Though invisible and impossible to touch, it forms the hidden skeleton of the universe, the gravitational framework that gathers gas, shapes galaxies, and orchestrates cosmic structure on the grandest scales. We know it exists not because we see it, but because we see its fingerprints everywhere, in the bending of light, in the speeds of orbiting stars, in the architecture of galaxy clusters. But the massive early galaxies discovered by James Webb pose a profound challenge to this invisible scaffolding. These colossal systems appear to sit inside enormous dark matter halos, gravity wells large enough to gather and bind trillions of stars. The problem is simple. Such halos should not exist this early in cosmic history. According to modern simulations, the first dark matter halos in the young universe should be small and rare. They need billions of years to grow through mergers and slow gravitational feeding. Yet Webb has revealed gargantuan halos seemingly formed in a cosmic instant. This leaves researchers with two uncomfortable possibilities. Dark matter may behave differently in the early universe, perhaps clumping more efficiently or collapsing more rapidly than our models allow. Our simulations are missing crucial physics, unknown interactions or processes that accelerate structure formation. Some scientists suggest that dark matter might have been denser or more tightly bound shortly after the Big Bang. Others propose self-interacting dark matter that could speed up halo formation and solve the timing paradox. Either idea would require rewriting core elements of cosmology. Meanwhile, the tired light alternative proposes an entirely different escape route. If the universe is nearly twice as old as the Big Bang model claims, around 26 billion years instead of 13.8, then early dark matter halos have all the time they need to grow enormous. In this view, what appears to be a young galaxy is actually ancient, its true age hidden by the redshifting effects of tired light, rather than cosmic expansion. A universe twice as old would allow dark matter halos to mature, merge, and accumulate mass over vast stretches of time. The impossible galaxies discovered by Webb would simply be old giants masquerading as newborns. But even this expanded timeline must still account for all other dark matter evidence, from the rotation curves of spiral galaxies to the gravitational lensing signals carved into the fabric of spacetime. Changing the age of the universe solves one puzzle, but risks unraveling dozens more. The early galaxy discoveries have therefore added intense pressure to the hunt for dark matter. Every new observation tightens the constraints on what dark matter can and cannot be. The most ancient collision in the cosmos. One of Webb's most extraordinary findings is the most distant galaxy merger ever observed, a titanic collision occurring 13 billion light-years away. Like two cities smashing together in slow motion, the galaxies twist and distort each other, flinging out vast tidal streams of stars, while their central black holes spiral together on a deadly dance that will end in a burst of gravitational waves. Galaxy mergers are some of the most dramatic events in the universe, cosmic car crashes unfolding over hundreds of millions of years. Yet this ancient merger presents the same riddle found across Webb's discoveries. How does such an enormous collision happen so early? For two massive galaxies to collide, both must first form independently, grow large, and drift close enough together for their gravitational fields to begin a merger. This requires immense time the early universe, as we currently understand it, simply did not have. But here they are, fully formed, massive, already colliding. This single cosmic smashup reinforces the broader crisis. The early universe looks far too mature.
The two galaxies involved in this ancient collision aren't primitive or fragile. They are already massive, mature systems, packed with billions of stars, layered structures, and gravitational architecture that should have required ages to assemble. Yet here they are, fully formed and violently merging when the universe was barely 500 million years old. It borders on the impossible.
This extraordinary merger also reveals an unexpected portrait of star formation in the early cosmos. The colliding galaxies exhibit explosive starbirth regions, stellar nurseries generating new suns at rates far beyond anything observed in the modern universe. It suggests that interactions between galaxies are not rare, gentle encounters, but frequent, high-energy collisions in a cosmos far more turbulent than previously imagined. Simulations of this merger show that the final combined galaxy would eventually reach a mass comparable to the Milky Way, but our galaxy required over 13 billion years to accumulate its stars through countless minor mergers and a patient trickle of star formation. How could the primordial universe accomplish a similar feat in a cosmic sprint? The collision also sheds light on the influence of supermassive black holes in shaping galaxies. Both merging galaxies host actively feeding black holes at their cores, monsters consuming gas at extreme rates. Their presence suggests that black holes weren't just end-stage relics, but active regulators guiding star formation and galactic growth from the earliest epochs. As astronomers dissect this 13 billion-year-old crash scene, it becomes increasingly clear that the early universe was a battlefield of gravitational chaos, not a calm nursery. Merger after merger may have accelerated galactic evolution to levels far beyond our expectations. The spectroscopic reality check. In astronomy, photographs spark mysteries, but spectroscopy solves them. By splitting a galaxy's light into a rainbow of wavelengths, scientists can decode its chemical elements, temperature, motion, and age. It is the ultimate truth detector. When astronomers aimed their spectroscopes at Webb's impossible galaxies, they hoped for clarity. What they found instead was a mix of revelations and shockwaves. Some galaxies that appeared monstrously large in initial images turned out to be quasars, supermassive black holes blazing so brightly that they drowned out the faint starlight of their host galaxies. These cosmic searchlights created the illusion of enormous galactic mass. But many other candidates passed every spectroscopic test with stunning clarity. Their spectra revealed enormous populations of mature stars, layered chemical signatures, and the hallmarks of well-developed galaxies. These were not illusions. These were real giants in a universe far too young to contain them. The chemical data was even more unsettling. Heavy elements like carbon, oxygen, and iron, materials forged only in the hearts of stars, were surprisingly abundant. In theory, multiple generations of massive stars must have lived, died, and scattered their enriched remains across space to create such compositions. This should take billions of years, yet these galaxies achieved it in a few 100 million years. Spectroscopy also confirmed the brutal truth that these galaxies were indeed 13 billion light-years away. Their light originated when the universe was in its infancy, ruling out the possibility that they were closer galaxies masquerading as distant ones. Even more surprising, the early giants weren't uniform. Some were raging star factories, others had already stopped forming stars entirely. This diversity revealed a complex galactic ecosystem that should not have existed so soon after the Big Bang. The spectroscopic data left no room for doubt. The early universe produced massive, chemically mature galaxies in a fraction of the time predicted by current cosmological models. And this crisis deepens when placed into the broader backdrop of one of the universe's greatest transitions, the era of reionization, long known but now far more puzzling than we ever imagined.
Reionization, one of the universe's greatest transitions, unfolded roughly 1 billion years after the Big Bang. During this era, the very first stars and galaxies ignited with such ferocity that they burned away the neutral hydrogen fog that once filled the cosmos. Their radiation carved out bubbles of transparency, gradually transforming the universe from an opaque haze into the clear, star-filled expanse we observe today.
The massive early galaxies identified by James Webb didn't merely participate in this transformation, they dominated it. With their furious star formation and hyperactive supermassive black holes, these primordial giants flooded space with enough ultraviolet and X-ray radiation to ionize enormous regions around them. They weren't just breaking theoretical limits, they were actively reshaping the physical state of the universe itself. Traditional computer models long suggested that reionization should have been a slow, gentle process, led by countless small, faint galaxies quietly chipping away at the cosmic fog over several 100 million years. But the discovery of enormous, energetic galaxies so early in time suggests a much more dramatic reality. Reionization may have been explosive, rapid, and violent. This new picture has consequences far beyond the study of early galaxies. A faster reionization timeline would alter when the first stars formed, how quickly supermassive black holes grew, and how early cosmic structures assembled. In effect, the entire evolutionary timeline of the early universe may need to be compressed. Recent cosmic microwave background (CMB) observations reinforce this possibility. Polarization patterns imprinted on this ancient radiation hint that reionization began earlier and progressed faster than standard cosmology predicted. This independent evidence strengthens the idea that the early universe was far more dynamic than previously imagined. Reionization also helps explain why Webb's early galaxies appear so intensely red. The radiation they unleashed heated and altered the surrounding intergalactic medium in a way that scattered blue wavelengths more strongly than red. As a result, even a relatively young galaxy could appear strikingly red and aged in infrared observations. As astronomers deepen their study of reionization through direct observation and advanced simulations, the process is emerging as a critical bridge, connecting Webb's impossible early galaxies with a broader, more radical understanding of how fast cosmic evolution can proceed under extreme conditions. When the evidence stacked too high, as discovery after discovery mounted, a growing faction of scientists began to wonder whether the issue was not galaxy formation at all, but our foundational understanding of the universe itself. Perhaps the Big Bang model, despite decades of success, lacks something essential about the nature of time, space, and cosmic evolution. Alternative cosmologies, long pushed to the margins, suddenly gained new relevance. These models challenge ideas at the very heart of modern astrophysics, from the cosmic microwave background to the very concept of an expanding universe. One family of theories proposed that the universe is cyclical, not linear. In these models, the cosmos undergoes endless phases of expansion and contraction. Our current universe would simply be the latest in a long chain of cosmic epochs. With effectively unlimited time available, galaxies could form, evolve, and rebuild across countless cycles. Other models suggested that our universe might be embedded within a higher dimensional framework, a cosmic architecture with hidden dimensions and exotic physics. These dimensions could supply additional energy or matter, accelerating galaxy formation beyond what four-dimensional physics allows. The old steady-state cosmology, which once rivaled the Big Bang model, experienced a modern revival. Updated versions attempted to reinterpret the CMB and galaxy distributions while arguing that the universe has always existed in a roughly unchanging physical state. In such models, the redshift of distant galaxies might arise from mechanisms like tired light rather than expansion. But perhaps the most provocative proposals came from theories invoking modified physics in the early universe. According to these ideas, the fundamental constants, such as the speed of light or the strength of gravity, may have been different in the distant past. If true, the early cosmos could have operated under physical laws that naturally favored rapid galaxy formation. But each alternative faced enormous challenges. Explaining the full range of modern astronomical observations, from galaxy surveys to nuclear abundances to precision CMB measurements, requires models that are not only creative, but extraordinarily robust. Still, the impossible early galaxies discovered by Webb have reopened doors once thought forever closed. They hint that our universe may be stranger, older, more complex, or more dynamic than the story we've been telling for the past century.
Yet despite the strength of the standard cosmological model, Webb's discoveries revealed cracks in its foundations, places where the theory struggled to match the data. What once seemed unshakable now appeared incomplete. The growing crisis in cosmology opened the door to possibilities that only a few years ago would have been dismissed as unthinkable. As scientists explored these new frameworks, they found themselves confronting deeper questions about the nature of scientific truth and the limits of what humanity can truly know about the cosmos. Hidden beneath the spectacular images of ancient galaxies lies a subtler, equally crucial story, one told by the dust and gas that give birth to stars. Webb's infrared vision didn't just reveal the galaxies themselves, it exposed the chemical richness and physical complexity of their star-forming environments. Cosmic dust, though made of microscopic grains, plays an outsized role in shaping galaxy evolution. These particles absorb starlight and re-emit it as infrared radiation, warming the interstellar medium and influencing how gas collapses into new stars. In the early universe, however, dust should have been almost non-existent. It forms largely from dying stars and supernovae, processes that require time, lots of time. And yet the massive early galaxies discovered by Webb contain surprisingly large quantities of dust, far more than expected for their supposed age. This dust implies that multiple generations of stars must have already lived, died, and enriched their surroundings with heavy elements. In other words, stellar evolution must have unfolded at breathtaking speed, far faster than current theory allows. The behavior of gas within these early galaxies deepens the mystery. High-resolution spectroscopy reveals immense flows of gas streaming into galactic centers, fueling both rapid star formation and the growth of central black holes. These inflow rates exceed anything observed in the modern universe, hinting that early galaxies existed under physical conditions radically different from today. Simulations suggest that the early cosmos, with its higher densities and temperatures, may have allowed gas to cool and collapse more efficiently, enabling star formation at extreme rates. Many early galaxies showed disturbed gas dynamics as well, consistent with recent mergers or violent interactions. These chaotic environments may explain how such massive systems assembled so quickly. The dust and gas observations point toward a universe that was not merely young, but fundamentally more active, enriched, and dynamic than previously imagined. These tiny particles and invisible gases hold critical clues to understanding how the cosmos transitioned from simplicity to complexity in astonishingly short cosmic time. Gravity as a telescope. Nature also provides a remarkable gift to astronomers: gravitational lensing, the bending of light by massive objects, which acts as a cosmic magnifying glass. Some of Webb's most spectacular discoveries rely on this effect. When the light from a distant galaxy passes near a massive cluster, the cluster's gravitational field warps and amplifies it, making faint galaxies appear brighter or larger. This allows astronomers to detect objects that would otherwise be invisible. But lensing adds complexity. A galaxy that seems enormous might simply be highly magnified. To uncover the truth, astronomers must model the lensing effect with precision, determining how much the light has been amplified. Only then can they estimate a galaxy's true mass, brightness, and size. In some cases, lensing produces multiple images of the same distant galaxy.
each offering a different view of its structure and star-forming regions. Gravitational lensing has enabled astronomers to push observations farther back in time than ever before, revealing galaxies that existed only a few 100 million years after the universe's beginning. Yet it also highlights the delicate balance between observation and interpretation. The universe itself serves as both a laboratory and an instrument, but its lenses must be decoded before their secrets become clear. Reading the light of ancient stars. Every galaxy contains a fossil record hidden within its light. Stellar population synthesis, the art of reconstructing galactic histories from their spectral fingerprints, allows astronomers to decode this record. By analyzing a galaxy's colors, brightness, and spectral lines, scientists can reconstruct its star formation timeline, how many stars it contains, how old they are, and how quickly they formed. But for Webb's massive early galaxies, this analysis reveals something deeply puzzling. These ancient systems contain evidence of both very young and surprisingly old stars. Some seem to have undergone violent bursts of star formation, others assembled their stars more gradually. Even more shocking is the presence of red giants, stars that require hundreds of millions of years to evolve, appearing in galaxies that should themselves only be a few 100 million years old. Their chemical fingerprints deepen the mystery. High abundances of oxygen, iron, and other heavy elements reveal rapid cycles of star birth, death, and enrichment, far too rapid for standard timelines. Models suggest that these early galaxies may have had a top-heavy initial mass function, forming unusually large numbers of massive stars compared to galaxies today. These stars burn hotter, evolve faster, and enrich their surroundings far more rapidly, potentially explaining the high metallicity of early systems. As these models evolve, they paint a picture of a universe where star formation, stellar evolution, and chemical enrichment operated under physical conditions radically unlike anything in the modern cosmos. A tipping point in cosmology. With every new Webb observation, the anomalies began to converge into a single, unavoidable challenge. What started as a set of surprising outliers has grown into a systematic tension with the standard cosmological model. The early universe appears too structured, too massive, too chemically enriched, and too dynamically active too soon. This crisis marks more than a scientific puzzle. It represents a philosophical turning point. Webb's discoveries are reshaping how scientists think about cosmology itself, reminding us that every theory remains provisional, no matter how elegant it explains the past. The universe, as it turns out, still has the power to shock us, and perhaps our greatest discoveries lie not behind us, but ahead.
The current crisis in cosmology reflects the very skepticism that fuels scientific progress. To explain the existence of these impossible early galaxies, several competing hypotheses have emerged, each offering a different vision of the universe. Some scientists argue that the physics of early galaxy formation must be revised, suggesting that stars and black holes grew at rates vastly exceeding today's predictions. Others champion entirely new cosmological models that rewrite our understanding of space, time, and the universe's age. The debate has fractured the astronomical community into distinct camps, each defending a different interpretation of the evidence. Conferences, research papers, and heated discussions now routinely feature the early galaxy problem, with astronomers proposing increasingly bold ideas to bridge the widening gap between theory and observation. This paradigm shift also signals a broader transformation in how astronomy is practiced. The James Webb Space Telescope represents a leap in observational power, granting us access to epochs of the universe that were previously invisible. As Webb continues to deliver data of unprecedented clarity, the shift in cosmology may accelerate. Every new observation has the potential to disrupt long-held theories or reveal missing pieces that restore coherence to our cosmic timeline. Ultimately, this upheaval reminds us that science is not a collection of immutable truths, but a living process, constantly evolving as new discoveries reshape our understanding. The impossible early galaxies have pushed astronomers to confront the boundaries of current knowledge and consider ideas that seemed unimaginable only a few years ago.
Whether this shift leads to a full-blown revolution in cosmology or a refinement of existing theories remains for history to decide. What is clear is that Webb has pulled back the curtain on a cosmos far stranger, richer, and more complex than we ever anticipated. The evidence increasingly points toward a universe where the rules of physics operated differently in its earliest eras, where galaxies assembled at breathtaking speed, black holes ballooned far faster than expected, and the entire cosmic timeline may require rewriting. Whether these discoveries ultimately validate alternative models like tired light or force revisions to the Big Bang framework is still uncertain, but one fact is undeniable: the universe is refusing to behave the way we thought it should. Massive galaxies appearing far too early, supermassive black holes growing at impossible rates, chemical evolution occurring in fast forward. All of these phenomena challenge the foundational assumptions of cosmology. They remind us that, despite centuries of progress, humanity has only scratched the surface of understanding the cosmos. And Webb's mission is only beginning. As it peers deeper into space and farther back in time, it will continue to deliver discoveries that either heighten the crisis or unlock revolutionary insights about the fabric of reality. The saga of the impossible early galaxies is far from over. Future data will reveal whether these massive galaxies expose a fundamental flaw in our understanding of the universe, or simply represent the first evidence of a cosmos more intricate and astonishing than we ever imagined. As we venture deeper into the mysteries of space and time, we are forced to confront a humbling truth. The universe is not merely stranger than we think, it is stranger than we can think. The James Webb Space Telescope has opened a new chapter in humanity's quest to understand the cosmos, and the next revelations may eclipse even the discoveries that ignited this scientific upheaval. The impossible has become real, and our vision of the universe will never be the same again. Webb has shown us that the cosmos is neither orderly nor predictable in the way we once believed. From the moment those impossible red dots emerged in the cosmic dawn, we were confronted with a shocking possibility. The story we tell about the universe's birth may be profoundly incomplete. These ancient, massive galaxies, fully formed when the cosmos should have been in its infancy, have shaken our confidence in the Big Bang timeline and cracked open the door to revolutionary new interpretations of space, time, and the universe's age. The evidence is overwhelming. Across the early universe, galaxies that should not exist stand like monuments to the limits of our understanding. Whether they form through unfamiliar physics, inhabit a universe far older than we assume, or point toward completely new cosmological frameworks, these discoveries have transformed our cosmic worldview. We now stand at the brink of a new scientific revolution. The impossible early galaxies may represent only the beginning of a far greater transformation, one that challenges every assumption about our place in the cosmos. And the next wave of discoveries is coming. What secrets will Webb reveal next? What other impossibilities await us in the deep cosmic past? Subscribe and join us as we explore the unfolding mysteries of our strange, astonishing universe, where the impossible has become inevitable, and the journey of discovery has only just begun. The cosmos is calling, and at long last, humanity is ready to answer.